An interesting extension of the confidence intervals is here what we call the prediction intervals, which is really a form of updating. A little bit different than the Bayesian approach that we've talked about before, but it's in some ways a similar kind of take on things, and that is that we've collected a random sample, say x1 through xn. And remember that what makes a random sample is that these are all independent of each other. They're drawn from the same population pool. Okay, and here we're going to restrict this, that they're coming from a normal population, or at least something close to a normal population. Okay? And based on our data set, okay, we ask the question, what might we predict about our next data value that would come along, n+1. Right? And our point prediction would be that, well, it would just be equal to our sample mean. But what if we were interested in an interval prediction? Okay, and so let's define then what we might call a prediction error. And that is the n plus first value minus the sample mean. And ask a lot of the typical kinds of questions we've been asking when it comes, as soon as we define something new. What's the expected value of this new thing, this prediction error? Right? And in this case, expected value of n+1 is just going to be the mean, and we've already numerous times talked about the unbiased estimator, that is x bar, so that'll be minus the mean. So the expected value of the error is going to be 0. That's good. We always like error that's 0, right? And then ask the question, well, what's the variance on the error? Okay, and a variance of a sum is equal to the sum of the variances if they're independent, meaning the covariance is 0. Right? And of course the minus sign goes away for us as well as we get into that. So the variance of xn+1 is just going to be the population variance, and then the variance of x bar, remember, is the population variance divided by n. Larger than n is, the variance on x bar is going to go away, and if n is so large as to be infinite or equal to the population size, well then it should be the case that our sample mean will equal the true mean. Right? And if we factor that out, then we get the expression here that the variance for our prediction error is our population variance times 1 plus 1 over n. Of course, there again, as n gets large, then this gets closer and closer to 1. Right, so now we go and we say, all right, fine, let's define the z statistic equal to xn+1 minus x bar, right? So that's this whole prediction error, right? Minus its mean, but its mean is 0. So I'm not going to write that part down. Divided by then the standard deviation. So we'll take the square root of this, and that'll be sigma times square root of 1 plus 1 over n. Right, and that will be normally distributed with mean 0 and unit variance. Now if we have small samples, right, we replace sigma with our sample standard deviation. Right, so if we have large samples and we make this replacement, then we just get back to something approximately normal. But for small samples and replace sigma with S, then we're just going to go back to the t-distribution. And so now we have xn plus 1 minus x bar all over S square root of 1 plus 1 over n. And now we just conduct business as usual. To develop our confidence interval. Right. Now, the resulting confidence interval that you get, or really, prediction interval on xn plus 1, or really on the error, is not going to be particularly narrow, but if it were in the general, but if it does turn out to be that way, then that could be potentially good news. Right? And that means you have enough information that you can reasonably predict what the next value is going to be. Right? So these have perhaps only minor value. What the real value comes into play when you start doing some adding this in along with some other things that we'll talk about later on in the semester in the hypothesis testing segment.